Welcome to vlmd Rounds, a podcast on medical science and tools to optimize your health. I'm Dr. Vyvyane Loh. I am board certified in internal medicine and obesity medicine. My practice focuses on metabolic health to reverse chronic diseases, or better yet, prevent them in my patients. Since this is our first episode, I thought I'd start by introducing myself, but rather than just read you my bio, which you can find anyway on the website vlmdrounds.com, I thought I would share a vignette from my first year in medical school. So just some background, I attended Boston University as an undergraduate, and at the end of my freshman year, I was selected to be an MEDIC scholar. This was something you had to apply for. I think there were maybe 2,000 applicants, and they chose 12 of us for my year. And it was an immense gift because as an MEDIC, I don't remember what MEDIC stands for, sorry, but as an MEDIC, it meant that you had guaranteed acceptance into med school. So we had a guaranteed spot at BU School of Medicine. And this meant that for the 4 years undergrad, you were free to play and enjoy and explore intellectually. So as I said, it was an immense gift, and I took full advantage of it. I double majored in biology and classics and classical languages and literature. The total student enrollment at BU is about 30,000. I did mostly independent electives, so a class of 5 people was quite big for me. And in fact, most of my classes, especially in classics, were essentially one-on-one tutorials with my professor, who was also my advisor. It was a huge privilege. You can imagine then my immense shock, really a big cultural shock, when I got to med school. That first day, 200 students crammed into this small, stuffy, and may I mention, ugly auditorium. We had classes from 7 till 5 every day with a 1-hour lunch break, and it was just hours and hours of these horribly boring sessions. And I sat way at the back. No, I wasn't one of those who sat in the front. Way at the back. And I had a hard time connecting with the material because, to be honest, I think they were just trying to cram this stuff into you, get over the first 2 years and get to the clinical years, which was the real stuff in medicine anyway. And most people said you'd forget everything that you learned in your first 2 years. So I think that was the attitude. I didn't feel it was very much about learning. I was bored, I was uninspired. We had to do anatomy as well, and for that we had to do full dissection of the human body. So the anatomy lab was on the 14th floor. It occupied the entire floor, and it was surrounded on all 3 sides by these huge glass windows. And you had all these bodies laid out in rows. We were divided into dissection groups of 7. The lab was open 24/7, so you could go in and out, and you really spent long hours there dissecting out a nerve or an artery. You had to make sure you didn't nick something or cut something away by mistake. So I remember being in the anatomy lab, and one of the things you will never forget is the smell. It's just this overpowering, acrid, unbearable smell that clung to every pore and hair and fiber of you like a repellent coat that was sure to repulse anyone that came into contact with you. In fact, if you came from the lab down the elevator and those elevator doors opened, that smell would rush out at you. And most of us, I think, just burned our lab coats at the end of the first year because you just could not get rid of that smell. So there was this smell, the dreariness, the tedium. It was fall semester going into winter, so the days were short, it was dark, and I found myself on a rapid downward spiral. And then one day at lunch break, just on a whim, I noticed a church across the street from the med school. And this is a pretty rundown neighborhood, but I had not noticed this church before. So on a whim, I just went in. It was a Jesuit church, and I'm not religious. But when I walked in, the floors were white, the walls were white, and the church was flooded with this early afternoon, crystalline, pristine light that was just so beautiful. And it hit me at that point that for weeks and months, I had not seen anything beautiful. And that my experience in med school, that was one of the most heartbreaking things for me, that I had not seen anything beautiful. A few days later, though, I was back in the anatomy lab. It was probably late evening. I was working alone at my cadaver, though there were other students in the room. And I happened to look up. Just suddenly, I looked up. And something was different. I saw the rows of cadavers, a few students working, the fluorescent lighting, but something had changed, and I saw something quite different that I hadn't noticed in all the weeks and months prior. And this poem that I knew just rushed to mind and stuck in my brain. And I was just so taken by it that I couldn't forget it. So much so that a few days later, I found myself in a hardware store buying these huge rolls of transparent plastic and also colored markers. And then I went back to my apartment and spent the entire night just writing out this poem on the sheets laid out on my apartment floor. Now, mind you, I had not ever stayed up all night to study in med school, but here I was writing out this poem in its entirety, pretty long poem. And when I finished, I packed everything up and then lugged it all to the medical school, went up to the anatomy lab, and proceeded to tape this poem on the windows around the lab. I climbed onto tables and chairs and just taped this stuff there. And I finished just in time because that was when rosy-fingered dawn reached into the innards of this anatomy lab and flooded the room with pinks and oranges and gold. And this light began to dance with the words on the windows. And myself and the bodies were bathed in this light. And I remember standing there and taking it all in and watching this and looking and seeing something there that I hadn't seen in all those months before, in great delight. And I must have spent maybe 20, 30 minutes there, and it was time to go down for my first class. So very shortly into the first class, a security guard came in and said something to the professor, and the professor then made an announcement. There has been a security breach in the anatomy lab. An act of vandalism was performed, and the perpetrator should give himself or herself up because we will do a deep investigation. And I was thinking, huh? So I found myself at lunchtime going to the dean of students, and I knocked on the door. He's a very nice, kindly man. And I said, I'm here about the anatomy lab, the windows. And he said, it was you? And I said, yeah. He said, why'd you do that? I said, well, you know, it's this poem I wrote, and I put it, he said, you wrote a poem? It's your poem? You published your poem by, no, it's not my poem. It's actually by a famous American poet, but I thought it was really appropriate because it articulated something that I had not seen in all my weeks and months here. And I thought that it was important to recognize this along with all the stuff that we're learning in medical school. And I thought I wanted to share it with the other first-year students. And he listened and he nodded and he said, all right, no, I know you didn't, mean to do any harm, so just take down the poem, and that was a nice thought. And tell you what, maybe at the end of the semester you can just recite this poem, all right? Recite it at the end of the semester to your classmates, and that'll be very nice. And I looked at him and I thought, oh, I don't think they get it. So I thanked him. I said I would remove the poem, that I hadn't meant any trouble. And I also said, thank you, but I don't think I will be reading that poem to the classmates. I actually had decided to take another option instead, but that's a different story. Anyway, I went back to the lab. I started taking down this poem. And as I did so, I had a sinking thought. I thought, maybe I'm not really going to fit in. Maybe this is not for me after all. And that's quite a daunting thought, because after all, I was right at the start of my career as a med student, and I didn't know if that was the right place for me. So obviously I stuck it out, because I'm here now. But I must confess that over the years, there were quite a few times when I felt like I did taking down that poem in the anatomy lab. One of those times was when I noticed early in my career that the entire healthcare industry was really not about healthcare, but rather sick care. In other words, it was an industry geared towards delivery of medical care in the form of medications and devices and tests to manage chronic diseases. And really, it wasn't about attaining health at all. It was not healthcare, it was rather sick care, right? And this was crazy to me, because it was clear to all of us that most chronic diseases are preventable or even reversible, and yet nowhere in my training, not once in my education, did we ever talk about that. Well, in the end, I decided to start my own practice to do exactly that. I wanted to address the root causes of disease. And along the way, I found myself educating my patients, doing a lot of teaching. In fact, I teach a lot of classes to my patients. And over time, they started to ask me, well, Dr. Loh, how can I get this information to my family members? I have a sister or a brother in a different state or in another country. And how can I get this information to them so that they can reverse their diabetes or their high blood pressure? And I knew that at some point, I would need to do something to disseminate this information on a wider basis. And I did think about doing a podcast. But there was never really any time. I was busy. I was a sole practitioner, still am. And that was a lot of work. So I put that off for quite a bit. Well, it's still not the right time, but we're going to do it anyway. So here I am with this podcast. The intention is to really give you medical information and tools so you can focus on prevention of disease, you can focus on staying healthy. Now, for this first episode, I would like to talk about metabolism. My practice focuses on metabolic health, and so often my patients will ask, well, Dr. Loh, what do you mean by metabolic health? And by the way, what is metabolism anyway? So because I want to use this podcast to talk about nutrition and exercise and sleep and other environmental factors that are important to health, we need to have the foundation to understand how those things influence our health. And the thought was that we should start, therefore, with metabolism. All right, so this first episode, we will focus on metabolism. Let's go. All right, when you Google the word metabolism, there are a few things you come up with. This one is from Mayo Clinic. It says, metabolism is the process by which your body converts what you eat and drink into energy. Cleveland Clinic says, metabolism refers to the chemical or metabolic processes that take place as your body converts foods and drinks into energy. We'll do one more. This is Harvard Health. In simple terms, metabolism is the internal process by which your body expends energy and burns calories. Well, for me, metabolism is simply the regulation and management of energy flow within an organism. The regulation and management of energy flow within an organism. To make it shorter and maybe more succinct, we could say energy flow management in your body. I like that. Energy flow management in your body. Before I dive into a deep exploration of metabolism, I'm going to go over some basic science concepts. I'm not going to get too technical, but I feel we need to clarify some of these concepts because not everyone has a science background, and I want to get us all on the same page. All right, so the three elements I want to talk about are, first, atoms. Yes, we're going to get that basic. And then we're going to talk about membranes, number 2. Number 3, we're going to talk about codependent relationships. Yes. No, not that relationship between you and your mother. We won't talk about that. Other codependent relationships. All right? Way more interesting. Okay, let's start with atoms. So atoms have a central nucleus where you have the neutrons, and you also have positively charged particles that we call protons. Now, spinning around this central nucleus, we have negatively charged particles that we call electrons, and these spin around in these orbital shells around the nucleus. They don't really have a defined pathway, and we actually talk about the probability of finding electrons within certain orbital shells. Now, each orbital shell is associated with a certain amount of energy. So the further away an orbital shell is from the nucleus, the higher the energy, and then the closer to the nucleus, the lower the orbital energy. So if an electron were to move from a higher orbit to a lower orbit, for instance, it would emit or give up some energy in the form of electromagnetic radiation, right? Because it's moving from a higher level to a lower level, it doesn't need that excess energy, so it gives it off. On the other hand, if it were to go from a lower orbit to a higher orbit, then it would need to absorb energy in order to do that. Another thing about atoms is that within these orbital shells, they like to have paired electrons because it helps to stabilize the atom. If you were to have an orbital shell that had unpaired electrons, then it would make the atom unstable, reactive, kind of jittery. So it really likes to have paired electrons in their orbital shells. If you take, for example, hydrogen atom, which has one proton in the nucleus and one electron, it really wants to have 2 electrons in that orbit, but it's only got 1. And so a good solution would be maybe to find another atom, another hydrogen atom, let's say, and form an alliance with it. And in doing so, they could actually share electrons such that now that hydrogen would have its own proton, its own electron, and also a second electron that it shares with the other atoms. Kind of cheating, but it works. So now it's got a pair of electrons in that shell. And the same goes for the corresponding atom, the other hydrogen atom, right? And when you do that, and you share electrons between these two hydrogen atoms, you form basically H2 or hydrogen gas. And energy is stored in this shared electron bond, right? When that happens, you form a bond, a chemical bond, as in James Bond, B-O-N-D, yes, bond. And you form this bond and energy is stored in that bond, and that stabilizes the atom as a whole. Another thing you should know about atoms, sometimes something can jolt it such that it would kick out an electron from its orbital shell. So maybe some energy hits the atom and bumps an electron out of its orbital shell. And as this electron is bumped out of its orbit, in nature there are these molecules that can pick up that electron, right? And it's usually a chain of molecules. What happens is the electron that's bumped off the atom gets caught by the first molecule, which then tosses the electron to the next molecule, which then tosses it to the following molecule, and so on down a line. So there's a chain of these molecules. You pick up the electron with the first one, and then you toss it down the line. And at the very end of the line, you have the hoop, right, which would be known as the final electron acceptor. So you get all the way down, and then the last molecule at the line throws it into the hoop, which is the final electron acceptor. Okay. Now, when that happens, right, and you have, let's say, all these electrons being jostled off atoms and flowing onto these molecules, which form this chain, an electron transport chain, right? And you have this movement of electrons down this chain, this flow of electrons. You essentially have a current and an associated magnetic field. All right. So the takeaways here are atoms have positively charged protons in the nucleus, and they also have negatively charged particles called electrons, which spin around the nucleus. And they don't like to have unshared electrons, the negative charges, in their orbits, so they will often try to share electrons with other atoms, and in doing so form bonds and store energy in those bonds. Atoms can also get electrons kicked off them, and these free electrons then can be picked up by molecules, a chain of molecules called an electron transport chain. And the electron is transferred from one molecule to the other until we get to the end electron acceptor, the final electron acceptor, which you could visualize as the hoop. All right, that's it for atoms. Let's move on to membranes. Membranes are essential for life because we need to define an outside versus an inside, right? Because when you have a cell, you need to have a means to control the entry and movement of substances such that you prevent maybe the entry of noxious substances and toxins, right? And you can hoard resources within the inside. You can also protect yourself from infectious agents. And also, you could set up some kind of gradient between the outside and the inside, right, such that you form an energy potential along the membrane or along the border, which in this case is the membrane. So that's why membranes are really important. And we're used to thinking of membranes separating a cell from the external environment. But we can also have membranes within the cell. So you can think of the cell as having separate rooms and compartments. And let's say we have a playroom, and we can then put the kids in the playroom, have them play in there, make as much noise as they want. We'll shut the door, and that noise won't get to us in the office, right? So it's useful to have these compartments within the cell that will form separate environments for biochemical processes and to degrade substances, for example, to make substances without interference from other parts of the cell. So we talked about membranes. They are essential for life. We have external membranes separating cell from the external environment, but we also have internal membranes within the cell to form different cellular spaces or rooms within the cell for biochemical processes. And these membranes allow for control of movement between one space and the other of various substances. It can act as a protective barrier, and it also allows for the formation of an energy potential between one side of the membrane and the other. All right, that's it now for membranes. Let's go on to number 3, codependent relationships. I know you were waiting for this one. Well, millions of years ago, there was a simple little fellow, a prokaryote. It was a single-cell organism, bacteria, didn't have a nucleus, and really didn't have much going for it. Although he was very skilled in one thing, he was very skilled in some biochemical processes to make molecules as a form of energy storage. One day, this fella decided, it's really harsh and cold out here in the big wide world, and I'd really like to move into a bigger cell and get some protection and refuge from the big cold world. So if I move in there, maybe it'll be a safer environment for me, it'll be a little easier, and I can help out and pay rent, so to speak, by doing some biochemical work for that bigger organism, and maybe he'll let me stay. That's one version of the story. The other version was this bigger bacteria looked around, saw the simple little fella and said, well, that's good lunch, and went gulp, took in or ate up, swallowed up the little guy, and then found out that, hey, you're pretty useful after all, because you're capable of doing some work that I don't have to expend energy doing. And maybe we could work out a deal. You could stay here if you do this work for me, and you don't have to pay rent. I'll let you stay here. How about that? Okay, whichever way you take the story, this is how chloroplasts and mitochondria came about. They were essentially these simple organisms that somehow got incorporated into larger cells that had a nucleus. These were called eukaryotes. And in plants, these bacteria became organelles that are now called chloroplasts. In animals, they are now organelles called mitochondria. Mitochondrion, singular, mitochondria, plural. And what's special is that these organelles can perform biochemical processes that are very helpful to the cell, so that it's useful to have them stay in the cell. They are not exactly the same, but they are strikingly similar in so many ways, as we shall see in a little bit. What defines these organelles would be their membranes, and they have these special membranes that contain proteins within them that can help perform those biochemical processes. All right? So in plants, as I said, they are chloroplasts. In animals, they are mitochondria. And this process of a bigger, of two organisms coming together for mutual benefit is called endosymbiosis, right? Symbiosis having two organisms work for mutual benefit, which I think is great for all relationships, right? What you don't want is a parasitic relationship. Yeah, don't want those. But symbiosis is good. So this is endosymbiosis. All right. So now we've talked about, let's see, the atom, we talked about membranes, and we talked about those codependent relationships. Onward. Now we're ready to talk about energy. So we have energy from our sun, which gets to us in the form of light. Sunlight penetrates our atmosphere, comes down to earth, and strikes a leaf on a plant. All right. Now within the leaf, we have cells that contain chloroplasts. Remember those organelles that we just talked about? These chloroplasts have within them these inner membranes, as I said. And these inner membranes are stacked up, and they contain many proteins, but they also contain pigment molecules, such as chlorophyll. There are other pigments as well. We'll just use chlorophyll here, right? So we have the chlorophyll pigment on these membranes, and sunlight comes down and hits that pigment molecule and excites it, and that kick from the light energy really bumps an electron off the pigment molecule. Now this electron that's bumped off gets caught by other molecules. These are proteins that are in the membranes, this inner membrane called the thylakoid membrane. So it catches the electron that was jostled off the pigment molecule, chlorophyll, and it starts now to transfer it down the chain, just like a regular electron transport chain. So it grabs that electron, tosses it to the next protein, tosses it to the next protein, and so forth, until it gets to the final hoop, which in the plant is a molecule called NADP. All right, so let's go back first of all to that chlorophyll that had the electron bumped off. It's not very happy about that. So it's sitting there going, I can't believe that. That light molecule just bumped an electron off me. I just lost an electron. Now I'm going to have to find another one. And it looks around and it sees water, a water molecule, H2O, and it says, great, that'll do. And it grabs it and splits the water, the H2O, and grabs an electron from it. And now it's happy. It says, aha, I found an electron to replace the one that got bumped off. Yay, but very soon light comes and bumps this new electron off as well, and it drops into the electron transport chain and gets transported down the line, and the pigment molecule goes, drats, grabs another water molecule, splits it, grabs an electron, yay, light comes, hits that, and this keeps going on. So we split water, we use up water in order to replace those electrons in the chlorophyll. The other thing that happens is the O in the water, H2O, remember, is made into oxygen. So we use water, but we make oxygen as a result. Now, remember the electrons are flowing down this chain. And when you have a flow of electrons, you have a current, you have energy generation. And the protons from the water are then pumped using this energy from one side of the membrane to the other side of the membrane, what we call the stroma side, sort of the outer side of the membrane. And as we do so, we now generate a gradient, right? There's a difference between the inside and the outside. So the hydrogen is going to accumulate on the outside. So you have a lot of H's there, which basically impacts the pH, the level of acidity in that part of the cell. The other thing is we have an accumulation of positive charges on that side. So now we have an electrochemical gradient. In essence, we've kind of started to form a little battery along this membrane. Remember that final electron acceptor that I said was NADP. Well, NADP is that final hoop. The electron goes there, and NADP also takes with it a hydrogen, and as a result becomes NADPH, right? And so it carries energy in the form of that electron and also the hydrogen in that bond. And NADP is an energy carrier loaded up now with the electron and the hydrogen. Embedded in the membrane also is a motor, because as I said, we've started to form this electrochemical gradient and we've set up a little battery there. And we can now use that battery to run this motor. And the way it works is, so we have accumulated all the protons on one side of the membrane. And as a proton is pumped back towards the more negative side, the other side of the membrane, right? This allows for energy that the motor can use. And what it does with that is it takes a molecule called ADP, adenine diphosphate, two phosphate bonds, and it's going to add a third phosphate bond to it so that it becomes triphosphate. And in doing so, it's going to store energy in that bond. So we now have ADP turned into ATP with some energy loaded in that bond. So ATP is also another energy carrier in the body. And we can think of ATP and NADPH as currencies sort of within the body, right? They are currencies of energy that can now disseminate and move to different parts of the body, and you can use them to spend on doing work. So it's sort of like you go to work and you convert your work into your salary, into money in the form of salary in some currency. And then let's say you want your lawn to be mowed. So you can spend some of that money to get that work done for you, right? So in essence, you can use that ATP to do some biochemical work as well in different parts of the body, right? So now we have used the energy from sunlight and changed it and stored this energy essentially in these special molecules. And that really makes the chloroplast a kind of transducer, which is a device that converts energy from one form to another in order to do work. That's essentially what it is. Okay, now we have this energy. What are we going to do with it? So the plant looks around and says, well, you know, I think I'd like to make something. Yeah, I really like to make something. And it notices the carbon dioxide around in the atmosphere, and it says, you know, I really like that carbon dioxide. I would really like some of the carbons from there, and maybe we'll make something out of it. And so it decides to take the carbon from the atmosphere and bring them together, link them up into a molecule. And this molecule happens to have 6 carbons linked together, and it is a sugar molecule called glucose, right? And obviously, we have energy stored in those bonds. So this process of linking the carbons together into this 6-carbon molecule called glucose occurs in the stroma as the Calvin-Benson cycle. You don't have to remember that. We won't go into details there. But this is also the process known as carbon fixation, because we're taking carbon dioxide from the atmosphere in order to get those carbons. Remember also that we're using the ATP and the NADPH generated along that electron transport chain for energy to make this glucose molecule. Now imagine that a cow comes along and decides to chomp into the grass or leaf, and as a result it digests the plant, and the glucose gets absorbed into the bloodstream and eventually enters the cells of the animal. when glucose goes into the cell is really happy. It says, yay, energy delivery at last for the day. What are we going to do with this energy? So it looks at the 6-carbon molecule and says, well, it's kind of a big molecule. Maybe we should chop it up because there's energy stored in bonds, remember? So if we chop up this molecule, we can release some of that energy. So we'll take the 6-carbon molecule and chop it up into 2 pieces of 3 carbons, right? 2 3-carbon molecules. And when you do that, there's energy released, and that energy is used to make more ATP within the cell, right? Because we have ADP in the cell, and as you release energy from the bond, then you pick up another phosphate group, make that phosphate bond, so we now have ATP, store the energy in that bond as the molecule is split. You can take this 3-carbon molecule that is now called pyruvate, and you can ferment it in the presence or absence of oxygen, and you will make a substance called lactate. And in that process, you also release more energy, which we now can take and store in yet more ATP formation, right? So we'll have ADP going to ATP and storing that energy that way. So this is a nice way to make energy. But there are other things that you can do with that pyruvate. And this is where it gets really magical. So remember, pyruvate is a 3-carbon molecule, and it is now going to enter the mitochondria. Remember that, our special organelle? Now, mitochondria have actually 2 membranes. They have an outer membrane, which is porous pretty much to everything. So things can go in and out freely through that outer membrane. But we have an inner membrane as well, which is folded and pleated over and over again to enlarge its surface area. And those folds and pleats we call cristae, C-R-I-S-T-A-E. Pretty name. So these cristae help to enlarge the surface area of the inner mitochondrial membrane. And this inner membrane, unlike the outer membrane, is extremely impermeable to substances. Usually you need some kind of a transporter or shuttle to get things in and out. So it's very selective as to what it allows in and out of that membrane. Pyruvate gets in, and when it does that, it actually gets another carbon removed, and it becomes a molecule called acetate. It's a 2-carbon molecule. It is also tagged with something called coenzyme A, and it becomes a molecule called acetyl-CoA. Acetyl-CoA. And it is the acetyl-CoA that enters what is called the Krebs cycle. The Krebs cycle, otherwise known as the TCA cycle or the citric acid cycle, the bane and dread of most medical students around the world. Because I think in a lot of cases, as a student, you have to memorize this Krebs cycle, and there are various substrates and metabolites that are part of the cycle, all these names. You have to remember how many ATPs are formed and blah, blah, blah. So that's a lot. We're not going to do that because that's not even important. Let's just look at the bigger picture, the concepts, right? What we're doing as we bring this acetyl-CoA into the cycle is we're going to start to continue this process of regulation and management of energy flow. Okay, so within the cycle, the whole magic of the cycle is that we have the formation of these different products within the cycle, but they kind of replenish themselves, which is why it is a cycle. It doesn't really need to be topped up, because if you run the cycle into completion within itself, it should top itself up, right? So acetyl-CoA comes in, and then it runs into the cycle and forms various byproducts within the cycle, and they have beautiful names. They have names like citrate and oxaloacetate and so forth. So, you know, it's kind of pretty. I always thought maybe you could name your dog malate or citrate, or if you had a grandson, you could call him oxaloacetate, because it's kind of a distinguished name, maybe? Yeah, not really. Okay, forget about that. But we don't have to memorize those names. The whole point is we make these various products, and in the process, what's really important is the harvesting of electrons and protons from this cycle. Because that's, again, what we're really interested in. So we run this pyruvate, which is now acetyl-CoA, into the cycle, and this cycle is really for the purpose of harvesting out electrons and protons, which we can now load onto certain energy carriers, such as NAD and FAD. NAD. Remember that? It's kind of like NADP, which we saw in the plant. So it's similar, except it doesn't have the P bit. And both are derivatives of B vitamins. But these energy carriers, NAD, will pick up the electrons and protons, right, that are harvested in this cycle. And what it's going to do now is transport them to where? You guessed it, the inner mitochondrial membrane. And when it gets there, it's going to unload the electrons onto the membranes. And encrusted in the cristae of the membrane would be these special proteins or protein complexes. And they are basically part of an electron transport chain. So they pick up the electrons that are tossed onto them, and they start transferring them to the next protein down the line, to the next protein down the line, to the next protein down the line, until we get to the final electron acceptor. Remember the hoop, which is in this case what? Yes, oxygen. Oxygen is the final electron acceptor in this electron transport chain in the mitochondria, which is why you need to take a deep breath, because you need that oxygen. All right, so as we're doing this, we're transporting the electrons down, and we form this flow of electrons. We now have a current forming, and we have energy to pump the H. Remember the NADH? Yeah, they unload the H, and the H's are pumped across and out of the inner mitochondrial membrane. So now we generate another electrochemical gradient with the H's on one side, so that the pH on the outside of the inner membrane is lower than the inside of the membrane. And we also accumulate positive charges on the outside of that membrane. And we are again setting up a battery, right, across this membrane. And it's not really a small battery, because it has an electric potential of about 200 millivolts, which provides an electric field strength of 30 million volts. Yes, and that is within your cells. Isn't that amazing? So this energy then across this membrane is set up to power, you guessed it, a motor called ATP synthase. Here we see it again. And this motor is used to make ATP. What happens is we set up this battery, and now as a positive charge, a proton, tries to flow back into the matrix side of the mitochondrial membrane, then that energy is used to power this motor, and it will take a molecule of ADP and form ATP, put energy in that phosphate bond. So you can see the similarities there with the chloroplast, right? Another thing I want to say is, remember those substrates that are part of the Krebs cycle? Well, they can be very useful too, because they can be used to take part in other biochemical reactions and form other substances. Acetyl-CoA, for example, is very useful in the synthesis of other organic molecules. So not only do we harvest the electrons and protons from within the cycle, we also have these substrates that can now be part of various synthetic and biochemical processes within the body, right? Really nice. Now that we have this big picture of metabolism, right, and this flow and regulation of that flow, energy flow within the body, let's think about what could go wrong. Because when we talk about metabolic dysfunction or disease, that's really what we're talking about. What is going wrong in this energy flow management, right? So, for example, let's say if for some reason you're just not able to harvest electrons and protons from the Krebs cycle. So what would happen? So you're not able to do that, then you really don't have anything to carry to the mitochondrial membrane, and then you don't set up that flow, or you have a very weak flow of electrons and really don't have a lot of energy across that membrane. So is that good or bad? Not good, obviously. All right, let's take another case. What if you don't have enough oxygen? Remember, oxygen is the final electron acceptor in that chain. So let's say you don't have enough oxygen for some reason, and what would happen? Well, we can have the electrons flow through the electron transport chain, but because we don't have a final electron acceptor, then the whole thing stalls. Basically, we transfer electrons, we go boink, boink, and then, oops, we don't have a final acceptor. And so the whole thing stalls, and we don't generate any electrochemical gradient. And basically, you have a flat battery. End of the line. Not good, right? Don't want to be without oxygen. Right. Or we could say maybe we don't have enough energy carriers. So for some reason, we don't have enough NAD, and we can't carry those electrons over to the membrane. Same thing, we're not going to have that flow of electrons, and so we'll have a flat battery. But what if we had the opposite problem? What if we harvested a lot of electrons and protons, and now they flood that membrane? Is that a good thing or a bad thing? Well, it depends. You know, if you think about it, these electrons are highly reactive, right? They're unpredictable, they're kind of jittery, and if you have a whole swarm of them at the membrane, they could actually cause a lot of damage. And we'll talk about this in a later episode, but that might not be a good thing if you flood the membrane with all these electrons, okay? So now you can start to see that it's not a good thing to have dysregulation of this energy flow, and this is what sets us up for disease processes. So when we talk about metabolic dysfunction, we are really talking about disruption of this energy flow management, dysregulation. All right, time for our wrap up. So in summary, what we learned today is that energy is stored in the bonds of food molecules such as glucose. And when glucose enters the cell, we access that energy by splitting bonds and loading the energy in carriers such as ATP, NAD, NADP. And the glucose now becomes pyruvate. It enters the mitochondria and the Krebs cycle. where electrons and hydrogens are harvested, loaded onto NAD, carried to the inner mitochondrial membrane, where the electrons are tossed onto the electron transport chain. And in doing so, we generate energy to pump the hydrogens across to the outside of the membrane, and we set up this electrochemical gradient. And this is a battery that we've set up to drive a turbine called ATP synthase, which is now taking energy when a proton, a hydrogen proton, drops down the energy gradient by re-entering to the matrix side of the inner mitochondrial membrane. And that energy is used to form ATP. It's stored in that ATP bond so that we can use that anywhere else in the cell. The Krebs cycle also has a lot of substrates that can be used for various other biosynthetic processes within the body. And if we have any dysregulation or disruption of this energy flow or backup of substrates, that's when we start to get into trouble and we start to see the initiation of disease. Okay, we've come to the end of our first episode. There's one more thing I'd like to do. I am finally ready, after all these years, to recite that poem. I'm not going to do the whole poem, it's very long. You can find that on the website, vlmdrounds.com. But I'll do the first section of that poem, and I hope you'll see the significance of that poem and what it meant to me as a young medical student. It is, of course, by Walt Whitman. So I hope you enjoyed the episode and that you'll join me for our next one. Signing off from vlmd Rounds, this is Dr. Vyvyane Loh, and I sing the body electric. The armies of those I love engirth me, and I engirth them. They will not let me off till I go with them, respond to them and discorrupt them, and charge them full with the charge of the soul. Was it doubted that those who corrupt their own bodies conceal themselves? And if those who defile the living are as bad as they who defile the dead? And if the body does not do fully as much as the soul, and if the body were not the soul, what is the soul?